Let us move into something interesting today, and that is vibrations. A word probably your teachers don't use, but this is the true area of study. It's a very, very interesting area. It's a very, very difficult area, and it's an area which is a must in life. My heart, when I put my hand on my heart, to and fro, to and fro, to vibrations. I will use these concepts of vibrations even to predict certain changes which can happen in my heart under certain conditions. And soon you will find that you can extend this concept into bigger and bigger scales, and you find that in life, everything has a certain cycle of repetition. Everything has a time period. It repeats itself. The seasons, the weather conditions, the movements, and that kind of understanding, that kind of symmetry, and that kind of language that most of the events in real life are periodic, whether it's climatic conditions, it's the weather conditions, it's your entire day and night situation, including the pulses and movements within your own self, your organs, your own life cycle. It's periodic. There's a birth, there's a death, there's a birth, there's a death. It's everything seems to be having a certain periodicity. I'm just extending it. But we're going to talk about very specific situations where we talk about vibrations, the ones I've been talking about. The branch of a tree swaying to and fro, the boat bobbing up and down. Or if I take a ball and I press it down, deformation. As long as I'm within the elastic limit, what happens to the ball when I remove the force? See? Vibration. Another word which is commonly used is oscillations. Another vocabulary word which commonly comes when we talk about vibrations, we talk about oscillations, is periodic motions. Or the examiner simply says to and fro motions. You want to visualize? Just think about this little ball in a bowl, hemispherical bowl, and just give it a push. Oscillations. It's a periodic motion. It's a to and fro motion. It's a vibration. More obvious situation. Pendulum. Periodic motion. It's an oscillation. It's a to and fro motion. See? A vibration created in the lab. some design component called a spring, engineering design, which has certain elasticity. I've connected a block to it and pull it and release it. Vibration, to and fro motion. I'm seeing oscillations, periodic motions. Periodic or repeats itself. Or I take a wire and I connect a rod to it and I twist the wire. I twist the wire and I release it. Oscillations, periodic motions, to and fro motions. See? Okay. This ball, I pressed it, part of the mass vibrated. What do I notice in all this? If you've been observing the examples that I've been throwing at you. All vibrations in life, all vibrations in life, all oscillations in life, like what you see around you within the human scales, can be bracketed into two groups. Linear oscillations or vibrations, linear periodic motions, or angular. Yes, you could have a combination of the two. No problems. Very complex. What we are going to do at our level of study is we will take a real-time situation and we will first try to cut off some of the constraints around, eliminate some of the constraints around, and put it in one of these categories. And then whatever in general we have learned about linear oscillations, we'll apply it to that. We will get a fair result of what we see in real life and what we have calculated on paper. So it is important that whether we are in linear oscillations or angular oscillations, we should have a certain vocabulary. First, certain wonderful definitions like amplitude, time period, angular frequency, frequency, and their relationships. Now we have a vocabulary, and I can fully define a linear oscillation, or if somebody is defining a problem to me which has linear oscillations, I will understand because I have got the vocabulary, I've got the relationships. Then to understand linear oscillations or angular oscillations, I create two very simple physical events. So I create a linear oscillator. I create a linear oscillator, which is nothing, which is just a spring which I buy from the market, or somebody has manufactured it for me, and I attach a rigid body to it, put it on a certain ground condition, and I create a simple linear oscillation, maybe along the x-axis. And by studying this in great detail, I will be able to take a real-time situation which falls in this category, and using the concepts I got here, I will apply it to the real situation. And to my surprise, I get a fairly good result. I'm able to predict for the real situation when it's going to fail, when it's going to break, when it's going to reach a certain stress conditions. Example, my building, which is swaying to and fro. I suddenly find that falls under this category. And so under extreme external force conditions, high winds and storms, if the amplitude reaches a certain value, it can break, because I have studied in my labs that for this condition, for this length of the building, for this mass, if this amplitude, maximum displacement, angular displacement, this particular structure reaches, it will topple. I can study that using my very simple experimental results. So just like I created a linear oscillator here, I think about what do I use for my angular oscillations, and I get a simple answer. The pendulum. And I use, to start off with, a simple pendulum. A thing, string, mass, bob, and dot, 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 dot. Angular oscillation. Linear oscillation. Angular oscillation. So my example will be this simple guy, which is the simple pendulum. I will study it, I will understand everything, all parameters involved, and similarly here, and then try and predict. By studying this to my surprise, I was even able to predict the elastic component of that branch which was swaying to and fro, to and fro. Oh, that branch was put in this category. And there was no way I could study the elasticity of that branch or that property which was giving it this particular feature, which was that within the elastic limit, that branch was going back to its original shape, size, everything. I will obviously study things under Hooke's limitations because the equations are so simple, because there is a direct proportionality between the forces and the deformations. I can easily develop mathematical equations and calculate everything that I need. Yes, it is a very idealistic situation, but to my surprise, I will be able to predict what would happen to my real-time situation. I cannot carry out an experiment with my real situations and make the building topple. So I make a prototype in the lab. I study the prototype. I make the prototype go through all extreme conditions. And then I make a note and I send it to the designer who has to design that building and tell him that please take care of this. Very good. Very, very good. Good. So it's simple now. All vibrations in real life are very, very complicated. All vibrations can be said are oscillations. Vibrations are periodic, they keep repeating themselves, to and fro motions. Then I said that I can bracket all of them into two classifications where I say linear oscillations or angular oscillations. Yes, I will have a mix of these two also. Though I don't study them at 10+2, but in real life there will be. The boat which is bobbing up and down linear is also going this way and that way. He's also having angular oscillations combined with linear oscillations. No problems. That's a little complicated case. That needs a little more of mathematics applications, which I will do after 10+2. Once I have built up this wonderful foundation, I can do it. I will only use those examples which can easily fall into this and fall into this, because that is what my course content is. And towards the end of the chapter of vibrations, I will study real-time vibrations where they get damped. The branch which is moving to and fro will after some time slow down and stop. It's a damped vibration. The energy got lost somewhere because of frictions and the vibration stopped. So towards the end, we will just in short mention and give a mathematical expression just for knowledge sake. We will keep it in our pocket, and wherever we get an opportunity to show a little bit of our knowledge during an interview, we will talk about damped vibrations and tell the examiner that you have gone a little more and you also know about vibrations, the real vibrations, which slowly the vibrations die off. Study. And once I've bracketed them into linear oscillations or angular oscillations, I realize that to keep it simple and to keep the mathematics simple, I stay within the Hooke's limitations or the Hooke's law, where stress is proportional to strain I find that what I have created now is simple oscillations, because the mathematics has become so simple. So I call my vibrations now, the real vibrations which are so complex, now I've simplified them. They are often referred to as simple oscillations. And as I go into more details, I start calling them simple harmonic oscillations or vibrations, or just simply simple harmonic motions. And in short, SHMs. Simple harmonic motions. Why harmonic? The word harmonic is to do with music. That's what our everyday language, we say harmonics is to do with music, isn't it? Then why do we call these vibrations harmonic oscillations or simple harmonic motions? Why not just simple oscillations and say that we are within the Hooke's law, and hence our vibrations, the mathematics of it gives us very simple to and fro motions, and that's it, story's over. Why do we go one step further and say these are simple harmonic motions and in short call them SHMs? Harmonics refers to certain periodic conditions which are connected to periodic functions and periodic functions we know. That is why we study them at 10 plus 2. We study them at 10 plus 2 because we need them in science, and especially in vibration, especially in certain to and fro variations. The current in my house which comes varies simple harmonically as a function of time. The voltage varies simple harmonically as a function of time. We also call it alternating currents, alternating voltage. Light wave also has the electric fields and the magnetic fields varying simple harmonically as functions of time. In a sound wave, the pressure pulse varies simple harmonically as a function of time. See how I'm extending the whole discussion of vibrations. And these functions, current as a function of time, current expressed in terms of time, electric current, electric field expressed as a function of time, magnetic field expressed as a function of time. Or simple motions expressed as a function of time, to and fro motions. These functions, which are periodic, which repeat themselves, then when life itself is periodic, weather conditions, this conditions, the rhythm of my heart, etc., everything, including the pulses and the currents which move through my body, everything is periodic. Then I need to have periodic functions, because tomorrow I would like to express the rhythm of my heart in terms of simple mathematical expressions. The rhythm of my heart is a function of time, a simple mathematical expression. Then what are these periodic functions? Periodic functions are the functions you have studied in great details. Trigonometric functions. All trigonometric functions are periodic functions. Sine, cosine, tan, cot, secant, cosecant. We needed to study these periodic functions because in life, everything seems to be periodic. Then tomorrow, if I want to express the weather over a span of time of 1 year, I need a mathematical expression. Then I can use trigonometric functions, because they are the only functions which are periodic. There is no other function which is periodic. They are the only mathematical expressions which are periodic. So if I want to put my entire observation in a mathematical format, make a mathematical model of my weather conditions, I need mathematics, I need trigonometry, and I have got to express the changes in temperature, the changes in humidity, the changes in all kinds of factors which are involved as periodic functions. I need these trigonometric functions. Good. My vibrations which I study, whether they are linear oscillations or angular oscillations, when I move and say I'm within the Hooke's limit, where stress is proportional to strain, and I say that now my vibrations have become simple, then when I mathematically look for mathematical functions, I obviously find that these vibrations are periodic, so I have to go into mathematics and look for those functions which are periodic. And automatically I go to the chapter of trigonometry and I start looking for all trigonometric simple functions which will agree with me. And to my surprise, I find that sine and cosine functions serve my purpose. They serve my purpose. All vibrations that I study, all simple vibrations that I study, all simple harmonic motions that I study, whether under linear conditions or angular conditions, can easily be expressed as functions of time, whether it's displacement, linear displacement, angular displacement, or it is the speed, the velocity of the object which is vibrating, or it's the acceleration of the object which is vibrating as a function of time. They all can be expressed as sine, cosine functions. And hence, the word harmonic comes in, because harmonic is connected with music. And if you look into the musical aspects, when you go into the vibrations of string musical equipments or air musical equipment, all the saxophones, or you go into all the string equipments or all the air equipments, from different kinds of flutes to different kinds of saxophones, you will find that those vibrations, the vibrations in the air, where the air particles are moving to and fro, the vibrations of the string in the string equipments, musical equipments, all those vibrations are nothing but, can be expressed as combinations of sine, cosine functions, periodic functions, and hence we say that they are harmonic. So we call these simple oscillations harmonic oscillations. Then the displacement of the particle which is vibrating as a function of time can be expressed as sine, cosine functions. The velocity of the particle which is going through to and fro can be expressed as sine, cosine functions. Maybe just sine, maybe just cosine, maybe sometimes a combination of sine, cosine. The acceleration can be explained as combinations. Acceleration as a function of time can be expressed as sine, terms of sine, cosine functions. Great. So now our study is going to be that we create a linear oscillator and we start getting mathematical expressions for displacement as a function of time, the velocity of the particle as a function of time, acceleration as a function of time. Then we get expressions for time period, the frequency, angular frequency, normal frequencies. Similarly, the angular oscillations, angles, to and fro motions as a function of time, the angular velocity as a function of time, the angular acceleration as a function of time. We find all of them can be expressed. When I go looking for periodic functions in mathematics, I come across the chapter of trigonometric functions which are periodic. And there, when I glean through it, I find that simple sine, cosine functions are sufficient. So I make a statement. Displacement, velocity, acceleration can be expressed sinusoidally. Sinusoidally. When you say they can be expressed sinusoidally, you mean you can express them as sine, cosine functions. As functions of time, remember. Where is the particle after 10 seconds? Position x with respect to time. What is the speed after 10 seconds? Speed as a function of time. And acceleration is what? Net force. Net force as a function of time. All can be expressed sinusoidally. Great. So much we have covered. Yes.
Sir,
Yes.
are there no other periodic functions other than these trigonometric ones?
Nope, not at our level at all. There might be many periodic functions which are just combinations of these.
Okay.
You see, what happens is trigonometric functions can be expressed in terms of even exponentials and logs and all, isn't it? If you
Yes, sir.
go further and further into the mathematics. But at the base level, it is just these functions.
Okay, sir.
I have studied my engineering and my sciences, and I moved from the bachelor's degree to a master's degree, and maybe I've done more, but I've not really probably got qualifications beyond the master's. But I'll tell you that these simple functions which you study at 10 plus 2, sine, cosine, tan, cot, secant, cosecant, they are 100% sufficient to take you through for the next 10 years.
Oh, okay. Yes, sir.
So you don't have to worry.
Okay. Yes,
I
sir.
never had a problem. But
Yes, sir.
I want you people, my discussion is, along with finishing whatever your syllabus says, my whole idea is to tell you where to focus when you are studying your functions and when you are studying your trigonometric functions. Now that I've told you why we study them, because real-time situations are periodic, you will give them more respect, isn't it? Let's take the simple oscillator. Remember, when I write vibrations, I'm talking of real-time vibrations. Now I'm just simplifying. Let's take the simple linear oscillator to start off with. Then we'll do the angular oscillator. So we create something in the lab. I draw the force diagram. Spring is most relaxed. What do you mean spring? We have studied springs to a certain extent. All my springs are hook springs. What do you mean by their hook springs? That means if I stretch my string, a spring force comes into play, and that spring force is directly proportional to the deformation or the elongation the spring goes through. Elongation I can write like this, but I prefer to write that elongation as this. Some elongation x. So I have a hook spring where my spring force is directly proportional to the amount it elongates. And if I give the spring force a direction, I put a minus, saying that the spring force always acts opposite the direction in which I expand the spring, I elongate the spring. So I elongate the spring this way, so my x is this way, then the spring force is this way. So I put the minus, see. When I put the arrow here. When I don't put the arrow, I don't put the sign, I say that the magnitude of the force is directly proportional to the magnitude of the elongation. When I put a direction, I put this minus. Very good. When I draw the graph of this, I'm explaining you my spring. When I draw the graph of this, and if I say that this is the spring force, and let us say I have aligned it to the x-axis, then this is the x. Then I find when x is positive, spring is negative. And when x is negative, spring is positive. So I get this kind of. It's a straight line graph because it's a direct proportionality. It's a linear relationship. Yes, I can do this. I can continue to do this. I can remove the proportionality and I can write by putting some constant here, proportionality constant. Hooke did that, but Hooke didn't really make a spring. Hooke created a hypothetical spring because he says a real spring which you buy in the market with those coils, that will not obey this rule. This is a hypothetical spring. This is a hypothetical spring. I don't know whether you like the word hypothetical. You can just say this is an ideal spring, Hooke spring, which obeys this rule. I've already told you earlier, many months back, that if you were to take a real spring and let us say I've taken this as a real spring. When you take a real spring, you find that this relationship between the spring force and x is like this. Yes, when x is positive, the spring force is negative. And when x is negative, the spring force is positive. But it's like this. When it is a curve, it means the relationship between the spring force and the elongation is in terms of square, cube, etc. I don't know what it is when I show it as a curve. That's a real spring, which you go and buy in the market, anything. The spring which you find in your little pen, click pen, or the spring which you find in your toy. All those springs, including the springs in your car suspensions. They will be like this. Some complex relationship between the spring force and x. But Hooke says, my spring, which is an ideal spring, which doesn't exist in real life, obeys this graph. So he says, if I have to work in the lab with a real spring. So when you work in a lab with a real spring, you only take this much portion of it. Only take this much portion of it. And you want to extrapolate it a little, you can, but you take only this much portion of it. If I have to use a real spring in a lab and take this much portion of it, you will find that when you do dot, 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 dot to find out how much extension I'm allowed so that this relationship holds, how much extension I'm allowed, it is surprisingly, it comes in millimeters. Imagine taking a real spring and then creating vibrations where you're only doing millimeters, then only the Hooke's law is obeyed. You better know your limitations in an interview because you're supposed to have done a lot of experiments and come. Okay. And remember the graph of a real spring also, please, just for knowledge sake. Okay. So I said TKR. I'll take a real spring, I'll stay within this little range where the extension is only in millimeters and I'll do my experiment, chalega yaar, right? And so you better know what you mean by an ideal spring, where this relationship holds, this graph holds, And if you have to take a real spring, you have to be very careful that you have to see that the elongations are very, very small. Okay, done, 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 done. Great. So let us draw the forces. Right now, the spring is most relaxed. And if I start, I fix this axis on the ground, not on this. Then if I start drawing my forces here where x is 0, no extension, I've coincided my 0 with this position of the object. Then the forces are mg and normal force. I extend it. When I extend it, I'll write down this later. When I now push this block a little, using my hand, some external force, I pull it. I've created some extension of the spring X. Now I draw again my free body diagram. I find mg remains mg, but n has probably become n dash maybe. No, we will write n only because there are no forces in this direction. So this always balances this. And if n is equal to mg, then n has to be equal to mg. Can't have n dash. So n dash has to be equal to mg. So n is equal to n dash. But I find that one more force has come into play, which is the spring force. As per this relationship, x proportional to the spring force, the size of the spring force, and the direction is opposite of x. X is this way. Since I'm discussing the dynamics only in the x direction, then I add up all the forces in the x direction for this particular situation. This is a dynamic situation because if I release my hand, this is going to start moving, dynamics will start. So I create a dynamic situation and then I start adding up all the forces in the direction in which the movements and the motions are there, which means in the x direction, and I find that the net force is equal to the spring force. Then according to Newton's law, the net force, the spring force should be equal to m into the acceleration. Since I've added only the x, then I remove this. Since I've added only the x, I remove this since this is in the x direction, and I remove this and I say this is in the x direction. But I find very soon that when I want to write down this spring force, now further, I find that the spring force, and when I write this in terms of motion, the motion was in this direction, or x was in this direction. So when I now further break it down, that spring force but is equal to kx, so I say kx, then acceleration is equal to mass. I come back to my problem and I say that my spring right now is massless, means the spring is very light and most of the mass is here. Later on, I will give the spring a mass and slightly change my equations, that's all, don't worry. So for the time being, it's this because I'm studying it. Then I write acceleration as dv by dt and I further write that but v is dx by dt. So I will get now equal to m into d square x by dt square. But now that I've written dv by dt, or I've written in terms of x, then the spring force and this are equal in magnitude, but they are not equal in direction. So I have to put my minus there. Just to tell you, it's that. Because after all, when I write my components, x components, I have to clearly state what is negative, what is positive. So I have to put the signs. But I would not put the signs because I was not sure about acceleration. But when I break it down, acceleration to velocity, I say, oh, velocity to ulta hai. Oh, x to this side ka hai, and force to this side ka hai. So I put the minus. Now I look at the equation in this form. Mx dt square equal to minus kx. Then I further say dx square dt square is equal to minus kmx. Then I shift this side. I get d square x by dt square plus km, some constants. This is some spring constant, which I'll explain you later on. This is some mass, and x is equal to 0. I look at this equation. And I say that this mathematics I have not done. Why has Mr. Patel, why didn't he just keep velocity and then x and all? No, I wanted to bring everything to x, and I wanted to have only x and t. I wanted to bring one variable x, and I wanted t, time. And this is some constant. Now I brought it to this stage, and I feel that I don't know how to move forward. I don't know how to solve this equation. What is this equation called in mathematics? Hitesh, any idea?
Sir, a differential equation?
Okay, it is a differential equation because this is also a differential equation. Then Hitesh, this is also a differential equation. Correct or not?
Yes, sir.
Then what is the difference between this differential equation and this differential equation?
Second degree differential equation.
Yes, this is a first degree differential equation. These kind of differential equations, solving them is part of your course at 10+2, which you will do when you are doing your calculus. It's very easy to solve this. You have to know integrals, of course. It's very easy to solve this. But when you come to the second degree, squares in this calculus have come. In this symbols, squares have come. That is not part of your 10+2 course. These are second degree differential equations which you will do when you go to your professional institutions. Oh God, how do I solve it? You can't solve it. You can't solve it. But one thing I would like to state, okay, you cannot solve it. You got a second degree differential equation. You are not able to solve and find out x as a function of time. Fair enough. Don't have to do it. There are other methods to do this. To get x as a function of time, there are other methods to do it. If you knew this, I would have done it. But I know that when a second degree differential equation, whether it is this or it is written as this variable with some other variable, these second degree differential equations They all have trigonometric solutions. They all have then the variables, whether it is y as a function of t or x as a function of t, they all can be expressed by sinusoidal functions. That means that if I were to solve the second degree differential equation, if I knew how to solve it, the solution would have been a trigonometric solution. X as a function of time would be a sine cosine function. So if I express S as sine function, if I express X as a sine t function, means if I express S as a function of time in terms of sine or cosine, it will satisfy this equation. If I put it on the left side, I'll get a 0. So I don't know how to solve it, but I know now that all second degree differential equations, the solutions are trigonometric. And further, they are sinusoidal. Okay, I can't solve this. No problems. No problems. I took you till here for a reason. Now, I raise this, 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 and I raise this, and I write, and I write, and I put it that the acceleration is a function of time. When x becomes 0, that means when the object comes here, acceleration becomes 0. So at this position, if ax becomes 0 at x equal to 0, that I say, but acceleration is nothing but m into acceleration is nothing but the net force in the x direction. That is becoming 0. That means that at x equal to 0, we say in physics, that is at equilibrium position. Net force becoming 0. If it was angular acceleration, net torque would become 0 at equilibrium position. So this is the equilibrium position, where the spring force is 0. That was the net force in the x direction. Yes, there is no spring force because the spring was most relaxed. So I conclude that for all vibrations, see, I'm making this general statement, there is an equilibrium position. Whether it is a pendulum moving to and fro, whether it is a branch moving to and fro, whether it is a boat bobbing up and down, there is an equilibrium position in every to and fro motion, in every periodic motion. There is an equilibrium position. What do you mean equilibrium position? Where the net forces and hence the net torques are 0. So if I knew the equilibrium position, and if I put that branch, I held it and I put it in the equilibrium position and I release it, it will not oscillate. Because I brought it to the point of 0 force, 0 torque. Same thing goes with the boat. Same thing goes with all vibrations. If you catch the equilibrium position and stop the body there, and now release it, it will not oscillate. But if it is not the equilibrium position and you catch the body at any position, other than the equilibrium position and release it, it will continue to oscillate. Because at that position, which is not the equilibrium position, there will always be a net force. And if there is a net force, there will be an acceleration, there will be a change in motion, there will be a movement. Now, the wings of a mosquito are having 600 oscillations per second, 600 vibrations per second. So you can imagine how fast it is vibrating. Can you find the equilibrium position? Impossible. Impossible. I will give you a simpler example. Take a pendulum, oscillating pendulum. Try and stopping it, thinking this is the equilibrium position, let's stop it and release it. It will still move. You will never be able to get the equilibrium position in real life so easily of any vibration. You can only theoretically calculate where it can be. This is one aspect I want you to understand. That every periodic motion has an equilibrium position. Every motion. Why did this object, just when I moved it, why didn't it just go on? Why did it come back? Just like every periodic motion has an equilibrium position. And second point, every vibration, whether simple or real, every vibration has a restoring force, has a restoring torque. Restoring force means when it's linear force. When it's angular, I will say restoring torque. There is a restoring force in every vibration. Restoring means if I displace it, it will try to restore it. If I displace it, it will try to restore it. And that is why the vibration is created. That is why the to and fro motions are created. That is why it is periodic. That is why it repeats itself. Because every vibration, there is something called a restoring force or a restoring torque. In every vibration, there is an equilibrium point. What do you mean equilibrium point? Where the net torque is zero or the net force is zero. Super. We are slowly catching, extracting things. I have not yet discussed second degree differential equation solution. I just took you there. Stop. I brought you back to normal. Oh, it needs a little more study. It needs a little more study. And so I said, this is not taking me too far. But I can still study this to a certain extent. Just give me a few more minutes, please. Yes. Simple oscillations which we talk about are sinusoidal motions. Please remember these terms, these are good terms to know. Let me quickly discuss the other features which I observed, which I could have some time in life already told you because we did take up springs to a certain extent earlier, but it is in this chapter that you will understand your springs very well. That if this was the x equal to 0 position, where we say, in short, we write equilibrium position, where the spring is most relaxed, then I find that my object moves and it reaches a certain position where now it stops. When I measure from my equilibrium position, that position where now it has stopped, the motion is zero, I find that it has gone through a maximum displacement in the positive x direction, and that distance I call the amplitude, and I give it a symbol A. So in every vibration that we study, real life, or when we simplify it with simple mathematics, and we study the vibrations within the Hooke's law, we will always speak about equilibrium positions, restoring nature of forces and torques, and we will always talk about amplitudes. Maximum displacement that the object goes through. Now, if this floor was having friction, then slowly the object amplitude would change and slowly the vibrations would be damped and they would die off because it's continuously losing energy and then it would run out of energy. Once I give it a push, then the amplitudes will keep changing because damped means the amplitudes will die off also. But if you recollect, when I drew the figure, I said this floor is smooth. No friction. I also now mention that the spring, if you really take a real spring and do this after some time, it becomes warm. So I will say no losses of energy in spring coils. So there is no loss of energy, or there is no loss on this floor on which this block is sliding. Frictionless floor. No friction in the coils also. So once I give it a motion, 10 plus 2 vibrations, for you to know. Once I give it vibrations, the vibrations will continue forever. And once I say the floor is frictionless and the springs do not have any friction in them, they do not heat up, then this object, when it goes to the extreme position, it will always cover the same distance all the time forever. So it did that, it stopped. But when it stopped, it just momentarily stopped. Because when I drew the forces, I got N, I got mg, but I also got a spring force, which was maximum because the spring force is proportional. Spring force is proportional. Spring force, the spring force is proportional to x. If x is becoming maximum, if x is becoming a, which is the maximum displacement, then the spring force is also becoming maxima. So there was a net force on this object. So it momentarily stopped and then it started moving in the direction of the net force. It again came to the equilibrium position. But by the time it came to the equilibrium position, it had gained a velocity. It had gained a kinetic energy. And so it overshot the equilibrium position. Once it overshoots the equilibrium position now, if I were to draw the free body diagram, I would get N, I would get mg, I would get the spring force, always restoring. And it would move till it momentarily again comes to a stop. Then to my surprise, if it is the linear oscillator which I have created, an ideal linear oscillator, where there are no frictions, nothing, where the vibrations continue endlessly, then I measure the maximum displacement in this direction, I find it is still equal to A in magnitude. In direction, minus A. In magnitude, A. Hi, Iqbal. Yeah, Iqbal, I know. I did give a missed call to you, but then I changed my mind. And right now I'm in a class. I'm just taking a class. Yeah. Bye. Yes. So the amplitude is a feature of this particular vibration because it always remains the same. These vibrations are endless. The maximum displacement is fixed. It's a feature. Now, for this ideal oscillator, as I study it, I find something else. Now, all that I'm saying is for an ideal oscillator, which is not valid for a real vibration, which I will distinguish. That in an ideal oscillator or the ideal vibration or the simple vibration that I have created, for which the equation is this, to my surprise, I find that when I start measuring the time t equal to 0, and when it goes to this position time, and then it comes back to this position, and then it goes to this position, then it comes back here, it has completed one oscillation. That time, the time has become t equal to capital T, which I call one time period. The time required to complete one complete oscillation, now it is ready to start again. Then I find that the time period is not connected with amplitude. It is independent of amplitude. What do you mean? I took the same spring, I took the same block. This time I just gave it an oscillation so that the maximum displacement was just A by 2. But to my surprise, I found the time period coming out to be the same. Then I made the displacement maximum only A by 4 and I released the object, so it started going where the maximum displacement was A by 4. Again I found out the time period. I was shocked. It's still T. The time period of a simple oscillator which I have created using the Hooke's law is independent of amplitude. It is dependent on certain other factors. When I look into it, I find that it is dependent on the elastic property of the spring. Then I find it is dependent on the mass. And as long as I don't change the mass and I don't change the spring, the time period remains the same. Whether I put this block on an incline, same mass, same spring, and I just create some oscillation with some amplitude, I find that the time period when I kept it horizontal was the same as this time period. Because it is dependent on the elastic property of this. It is dependent on the mass, which is the same. So will it be the same if I put the same spring and this block like this? Yes, the time period here is the same as this, is the same as this. My God, as long as everything is frictionless. This is amazing. Not only that, what is the definition? What do you mean by frequency, sir? Frequency was defined as the number of oscillations in 1 second. So I found out the frequency. I found out number of oscillations in 5 minutes. Then I divided those oscillations by 5 into 60. I got the oscillations per second. Number of oscillations per second. I got the frequency. And to my surprise, I found frequency also does not depend on amplitude. Time period doesn't depend on amplitude. But in the real vibrations, it does depend on amplitude. Time period depends on amplitude, frequency depends on amplitude. But in my idealized oscillation, it is independent. You guys at 10 plus 2 must remember this, because the examiner is going to bully you with that. He will put a spring block like this, then he will put a spring block like this. He will tell you, find the time period, find the time period, find the time period. And like a donkey, you will be trying to find out all 3 time periods. They are the same. They are only dependent on elastic property and the mass. These are the things where I want you to focus. Okay, sir? Fine. We were just studying. We will carry on next time. No missing classes. You guys miss class. In vibrations, you are really asking for